Hi, my name is Darian Hirotsu, and welcome to our NEC Software Defined Networking Technical Deep Dive series. In this video, we'll cover how to build a virtual SDN environment consisting of NEC's virtual PFC, or Programmable Flow Controller. As network engineers, with the growth and popularity of SDN, we're challenged with learning new technologies such as OpenFlow and the Open SDN concept featuring centralized control plane. This video is for engineers who want to get hands-on experience with these new technologies. Setting up the host virtual SDN environment. So recall the goal of this video is to show you how to set up a software-defined network on any host that you have available, such as a laptop or a desktop. We've divided this task up into 4 sections. First, in section 1, we'll cover initial host setup, meaning we'll show you how to verify that the host has enough memory, a disk space, and that the BIOS is set up correctly. And we'll make sure that you have all the proper pieces to get each virtual machine up and running in this virtual SDN environment. In section 2, we'll show you how to set up a Mininet virtual machine. And as a background, Mininet is an open source application to run OpenFlow switches and virtual hosts running an operating system such as Linux to generate traffic. In section 3, we'll show you how to configure the virtual PFC, or ProgrammableFlow Controller, which is the SDN controller for this particular environment. And lastly, in section 4, we'll show you how to build the SDN and integrate these virtual machines. And we'll show you how to configure an NEC virtual tenant network, which is a technology for network virtualization. So with that, let's go into section 1, initial host setup. Here with initial host setup, we've divided this up into 4 separate tasks. First, we want to verify host requirements, so we'll check that you have enough disk space, memory, and that the BIOS is set up correctly in order to run virtual machines for our SDN environment. Second, we'll show you how to download and install VirtualBox, which is a hypervisor or application that will run virtual machines. Next, we will show you how to submit the request to NEC to download the virtual PFC, which is the SDN controller for this scenario, and also how to acquire the trial license, which makes the virtual PFC function. And then lastly, we'll show you how to import the virtual PFC, which is downloaded in the previous step, to run that virtual machine. So with that, let's get right into this scenario. To start section 1, we're going to first verify the host requirements. We'll perform 3 steps to do this. First, we'll check to make sure we have enough storage to run the virtual machines. Second, we'll check memory. And then lastly, we'll check the virtualization setting in the BIOS to make sure we can spin up VMs. First though, talking about storage, as you can see in this Finder window, I have 70 gig available, which is more than enough disk space to run VMs. Just to provide a little background, if you want to be cautious, we're going to spin up 2 virtual machines. The first is the virtual Programmable Flow Controller, and the second is Mininet. Those 2 virtual machines have a combined provisioned disk space of 48 gig, so if you were to somehow accidentally fill up the virtual disks of both those VMs, as long as you have more than 48 gig, you're more than safe to run this lab. Next though, let's take a look at memory requirements. As you can see in this window, I have 16 gig on my Mac host. We've seen this lab work for hosts with as little as 4 gig, but if you're going to run a series of applications like your email client for work, along with these VMs, it would be best to have at least 8 gig available. Lastly though, let's take a look at the BIOS setting. Now if you run a Mac and Mac OS, or if you already run virtual machines using something like VirtualBox, you can skip this step. But if this is your first chance at spinning up VMs, what you'll want to do if you're running a Windows machine is reboot your box and then interrupt the boot sequence to drop into the BIOS menu. And as you can see from the screenshot, you should see a menu and a setting that looks something like this, and you're going to want to make sure that virtualization is enabled. So in a future step, if you were to have trouble spinning up a VM or powering on the VM, you might want to come back to the BIOS setting and just double or triple check to make sure virtualization is enabled. What I'm going to do next is change windows, and I'm going to show you how to install and download VirtualBox, which is the hypervisor used for this scenario. So as shown by this URL, we're at the download page for VirtualBox. Go ahead and download the installer for the relevant operating system that you're running for this scenario, and download the latest version of VirtualBox, and at the time of this video, that's version 4.3.22. Also, while you're here at the download page, it might be helpful to install the extension pack, and this contains a number of add-ons such as if you want to support or run virtual machines from an external USB 2.0 storage device, you can install this extension pack to support that. So when you're done installing VirtualBox, the next step is to submit a request for the virtual PFC trial, and I'll take you to another tab to show you how to do that. So note this URL up here to the left, necam.com/sdn/trial request. This is the page to submit the request for the virtual PFC trial edition. And once you fill out this personal information and click submit, you're going to wait a few hours and NECam support should respond with a follow-up email that has some pertinent information for the trial, which I'll show you in this next window. So what we're looking at here is the actual email from NEC support, and a couple things to point out. First, attached to that email should be a trial license, and what we're going to do is download this trial license and just make note of where you save it, because in a future video we're going to use this trial license to make the virtual PFC operational. And the second thing to note is the first hyperlink in the email, which is to a download page for the virtual trial programmable flow controller. And what I'm going to do is I'm going to switch tabs and I'm going to show you the download page so you know what to download. So when you click that hyperlink, it should navigate you here to this download page. And note that the virtual PFC is supported by a number of hypervisors. For this scenario, we're going to use VirtualBox, and we're going to download an OVA file that's supported for VMware, but we've tested the import a number of times and it should be just fine. So what I'm going to show you next, I'm going to change windows and I'm going to show you how to import this downloaded OVA. So go ahead and click this hyperlink and I'll show you what to do next here in this next window. So after downloading that VMware zip file, you're going to go ahead and unzip it, which will bring you to this directory. And within that directory should be the OVA file that you use to import to spin up the virtual machine. So I went ahead and launched VirtualBox ahead of time. So within the VirtualBox Manager, go ahead and navigate to File and Import Appliance. And from this window, we're going to navigate to the OVA file, as shown in the previous Finder window. And VirtualBox should populate some of the settings for the virtual machine. Go ahead and leave those as is. And if you want to run multiple virtual PFCs, you can go ahead and click this radio, which will reinitialize the MAC address of the NIC of the virtual machine. But once that's done, go ahead and click import. And this import should take just a few minutes. Now once the import is complete, we're going to next configure the network interface card for the virtual machine. So to do so, highlight the VM, and then click Settings, and navigate to Network. So for this scenario, we're going to use the bridge adapter, which is going to put the virtual machine in the same subnet as the local host. And in this case, my primary network interface of my Mac host is via Wi-Fi. Now there's a couple other options that are supported to run through this lab. You could also use NAT network, or you could use the host-only adapter. The primary reason that we're going to use the bridge adapter for this particular scenario is we need the virtual PFC and the Mininet VM to be able to exchange packets, and we also need the Mininet VM to have internet access so we can upgrade or update the version of Open vSwitch. So if you have trouble with whatever wireless network or whatever network you're on with the bridge adapter setting, go ahead and try a different option such as NAT network. Now once we've verified the network interface setting of the VM, we can go ahead and spin it up. So double click the VM in the VirtualBox Manager, and assuming the VM spins up and boots, then we're done with section 1. So since our virtual machine spins up and we get access to the console window, we know that virtualization is working and we can support virtual machines, so we can go ahead and wrap up section 1. In section 1, we completed our initial host setup. Recall the 4 tasks we just completed were: first, we verified the host requirements, meaning we checked memory, disk space, and the BIOS settings for our host to make sure it could support virtualization. We then downloaded and installed VirtualBox, or the hypervisor, for our virtual machines. Next, we submitted the request to NEC to download the virtual PFC or programmable flow controller for our SDN environment, and we acquire the trial license to make the virtual PFC function. And lastly, to complete this initial host setup, we showed you how to import the virtual PFC into VirtualBox. Section 2, setting up the Mininet virtual machine. Recall that Mininet is the open source application we're going to use to spin up our SDN topologies consisting of OpenFlow switches and Linux hosts. We divided this section up into 6 tasks. First, we'll show you how to download the Mininet OVF from GitHub. Second, we'll show you how to take that Mininet OVF and import it into VirtualBox or our hypervisor to spin up the Mininet virtual machine. Third, we'll show you how to log in to that Mininet VM. And then next, we'll show you how to uninstall the default version of Open vSwitch or OVS, which is the software controlling our OpenFlow switches. Next, we'll show you how to install OVS version 2.3, which is the recommended version from NEC to integrate with the virtual PFC or programmable flow controller for our SDN environment. And then lastly, we'll show you how to configure the Mininet VM to use OVS 2.3 by default. With that though, let's show you how to download the Mininet OVF. As you can see in this browser and this URL here, we're at the GitHub site under the Mininet project. And within the project, there is a page that provides downloads to zipped up versions of the Mininet VM. So for this particular video, the latest release of Mininet is version 2.2.0. And we're going to go ahead and download the 64-bit Ubuntu version of this VM. So when you click this, the download will start. And then for our next step, we'll show you how to import Mininet into VirtualBox in this next window. So I went ahead and downloaded the zip file beforehand. And when you unzip this, you'll end up with a directory. And within that directory is the OVF to perform the import of the virtual machine. So to show you how to do that, I have VirtualBox running here. And within the VirtualBox Manager window, go ahead and navigate to File and Import. And navigate to the directory and the OVF file. You'll see VirtualBox populate the configuration of the virtual machine, and much like we did in section 1, go ahead and reinitialize the MAC address in case we want to run multiple versions of Mininet. And once we're done, go ahead and click Import. To finish the import of our Mininet VM, our next step is set up the virtual networking for the virtual machine. To do so, we'll navigate to Settings and Network for Mininet. And recall from the first video, we're using the bridge adapter so we can be in the same subnet as the virtual PFC, and so we can have internet access for the Mininet VM. You could also use the NAT network feature for this exercise, or after you're done with section 2, you can switch over to the host-only adapter. But for simplicity, I like to use the bridge adapter for this scenario. And once you've set up the virtual network, go ahead and boot the virtual machine so we can log into Mininet. When you get to the login prompt, to log into Mininet, the username and password are Mininet, all lowercase. And as you can see from this output, we've received an IP address from DHCP. What I'm going to do in our next step is I'm going to show you how to uninstall the default version of Open vSwitch and how to upgrade to OVS 2.3.0. The reason for this, Open vSwitch controls the OpenFlow switches in this scenario, and OVS 2.3.0 integrates better with the NEC ProgrammableFlow Controller. And to do this, I'm going to switch windows and drop into Secure CRT since it's a little easier to run some of these commands from a terminal emulator. So first, this window is meant for access to Mininet, so I'm going to go ahead and log in to the Mininet virtual machine. And as you can see from the host name, we're in the Mininet VM. The first step to uninstall the default version of OVS is to run a command to remove the existing OVS packages. And I'm just going to use a cheat sheet here, since I've typed and tested these commands ahead of time. Our next step is to download the Open vSwitch 2.3.0 source code. And to do that, we're going to perform a wget for the tar file. And then we'll unzip the tar file so we can build OVS from source. So we're going to change directories into the untarred directory. And next we're going to configure the environment so we can compile and build Open vSwitch from source. So at this point we finished building OVS, and our next step is to make sure that OVS doesn't start a controller, because we want to use the SDN controller here as the virtual PFC. So the commands to do that are as follows. And then lastly, we want to make sure that OVS starts when the Mininet virtual machine boots. So the command to do that is as follows. And then finally, to make sure that the install was successful, we can check the version of OVS using this command. As you can see here, we've successfully upgraded Open vSwitch, so we're ready to conclude section 2. We have a working Mininet VM. To wrap up section 2, we just finished setting up the Mininet virtual machine. Recall, we downloaded the Mininet OVF from GitHub. Next, we imported that Mininet OVF into VirtualBox and set up the virtual network interface. Third, we logged into the Mininet VM. Next, we uninstalled the default version of OVS running in Mininet, and we installed from source OVS 2.3 to properly integrate with our external SDN controller, namely the virtual programmable flow controller for this scenario. And then lastly, to wrap up section 2, we configured Mininet to use that OVS 2.3 version by default. Next though, we'll show you how to set up the virtual PFC. Now that we've finished configuring the Mininet virtual machine, we're on to section 3, which is to configure the virtual programmable flow controller, which is the SDN controller for this scenario. We divided this section into 5 steps. First, we'll show you how to log into the virtual PFC and the default credentials. Second, we'll show you how to stop the PFC software processors. This is a necessary step for the third piece, which is to reconfigure networking on the virtual PFC. The purpose of the third step is the virtual PFC comes with a static IP address configured by default. We want to be able to have the virtual PFC access our virtual machines on our local environment as well as reach the internet. Fourth, we'll show you how to reboot and verify the PFC's software processes. And lastly, we'll show you how to install the trial license we acquired in section 1 to make the virtual PFC function correctly. First though, let's show you how to log in to the virtual PFC. We're starting this video from where we saw in section 1. We have the virtual programmable flow controller booted up, and we're looking at the console from VirtualBox. So our first step is to log in to the virtual PFC. To do so, we'll use a default username and password of root and a password of PFC, all lowercase. If needed, you can refer to section 1 of this video, where we showed you an email from NEC support, and that'll have some links to documentation with the relevant default logins. Once we've logged in, we'll take a look at the current networking configuration, and note that the virtual PFC comes with a static IP. Since this virtual PFC is going to reside on our local LAN, we need to reconfigure networking, and a prerequisite to do so is to stop the PFC cluster process. And to do so, we can use this utility, PFC stop cluster. Once the cluster process is stopped, we're ready to reconfigure networking. We can use this utility, PFC net setup. And if you're familiar with Linux, you may be tempted to reconfigure networking by manipulating the flat files. However, if you use the PFC net setup utility, you'll ensure that any new configuration is correct. So within this menu, we'll go ahead and select 3 for interfaces and 0 to change ETH0. Within this submenu, we'll be reconfiguring ETH0, so we'll select Y to activate on boot time. We're going to select Y to use DHCP. We'll leave the firewall running, and we'll use the default IP MTU of 1500. We'll confirm all settings are correct, and then we'll exit this submenu. So we're back at the default PFC net setup menu, and first we need to save this new profile, and then we need to activate. We'll be prompted to confirm the activation, and the reason is we're going to restart the networking process on this virtual machine. Once networking has been restarted, we'll hit enter to return to the menu, and then we'll exit. And at this point we can confirm the networking change. And as you can see here, we're in the 10.0.1/24 subnet, so we're in the same subnet as Mininet as hoped. So our next step is to finish this reconfiguration of networking. What we're going to do now is we're going to change the host file just for consistency, since our local host now has a different IP address. And then lastly, we need to reconfigure the PFC cluster configuration. So there's 2 columns here worth noting. First is the committed data, which is the current running config. And see here we have the original static IP address. And in the column to the right we have the registered data, and this is where we're going to apply our new configuration. So to do so, we're going to use this utility, PFC setup cluster config, and -s refers to the current configuration, which is a host name of all lowercase PFC, as shown here. And to apply a new registered configuration, we'll use the -r argument, and we'll leave the host name as all lowercase PFC. Next step is to change the IP address, and recall we have an address of 10.0.1.20. And as you can see here under registered data, we now have the new registered configuration. To commit, we use the same utility, and we pass it the argument -f for force, since as you can see here, we are only running a single PFC since this is a trial edition. In production, you would have a second PFC for redundancy. So we're using -f to indicate that we're going to run this in a standalone. Once that is done, we'll go ahead and reboot to restart the PFC software processes, and we'll wait for it to come up to verify. Now that the PFC is rebooted, we'll log back in. Now using the PFC show cluster status command, we can check the status of the virtual PFC. And init means the PFC is still starting its software process, so we'll have to wait just another minute or so. And when we see status and ACT for active, our PFC is ready to accept OpenFlow connections. Now there's one more step in order to fully set up the ProgrammableFlow Controller, which is to install the license. And I'm going to change Windows because we're going to do this from Secure CRT. So So in this window, I'm going to log in to the virtual PFC. As you can see from the prompt, I'm now logged in Secure CRT. Recall in section 1 of this video, we downloaded the trial license from the email we received from NEC support. And what I'm going to do now is I'm going to copy the trial license, where I saved it in my download folder, over to var temp of the ProgrammableFlow Controller. I'll just do a quick check within the directory to make sure the file transferred correctly. And the next step is to install the license. And we can use this utility, PFC License Management. First, I'll just do a list to see any current licenses, which there are none. And then using the same utility, I can do an install and pass it the trial license as an argument. And as indicated here, the license has been installed. We'll just do a quick verification again. And as noted from this output, we have a working license. So at this point, we're done with section 3, and we have a working programmable flow controller. Wrapping up section 3, we just completed configuring the virtual PFC. We showed you first how to log in to the virtual PFC. Second, we showed you how to stop the PFC's software processes, which is a requirement for our third step, reconfiguring networking. Recall our virtual PFC comes with a static IP address by default, and we need to reconfigure networking to have it access our local LAN. Fourth, we showed you how to reboot and verify the PFC's software processes after the networking change. And lastly, we showed you how to install the trial license to run software-defined networking scenarios. In section 4, we'll complete our build of our virtual software-defined network, and we'll configure our first NEC virtual tenant network. This section is broken out into 5 steps. First, we'll show you how to run Mininet, which will spin up an OpenFlow switch and 2 Linux hosts. We have a diagram showing you the scenario here shortly. Second, we'll show you how to configure Linux host interfaces in Mininet so you can configure more complex scenarios using VLAN tagging. Third, we'll show you how to configure an NEC virtual tenant network. For those familiar with MPLS VPN technologies, a VTN provides layer 2, layer 3 connectivity, similar to MPLS layer 3 VPN and VPLS. Fourth, we'll show you how to verify host connectivity for hosts in Mininet so you can pass traffic over the OpenFlow switch. And lastly, we'll show you how to perform some basic OpenFlow troubleshooting. When we finish this step, you'll have a working virtual SDN environment. First though, let's show you the topology for this scenario. Our diagram here shows our VirtualBox hypervisor and 2 virtual machines. To the left, we have our virtual PFC, and to the right, we have Mininet, which has spun up an OpenFlow switch and 2 Linux hosts, H1 and H2. The OpenFlow switch, S1, shares an IP address with a Mininet VM, and the virtual PFC gets its own unique IP address in the same subnet. This represents our control plane, and this interface will be used to exchange OpenFlow control plane messages, such as flow mods. Shown here in red, we have the data plane. These are 2 virtual interfaces spun up by Mininet, and this will allow us to send traffic between H1 and H2 to see how OpenFlow operates. Let's go ahead and show you how to build out this scenario. In section 4, we're going to integrate all of the pieces from sections 1 through 3 to build our first software-defined network and configure our first virtual tenant network, or VTN. We'll talk about VTNs a bit more in detail in a future step, but first let's show you how to run Mininet and launch the topology we showed you in the introduction. As you can see here, I went ahead and logged into the Mininet VM ahead of time. This command here launches the topology of a single OpenFlow switch and 2 Linux hosts. We need to point the OpenFlow switch to the SDN controller. In this case, we're using the virtual PFC. So as a reminder, I'm going to switch tabs in Secure CRT to the virtual PFC. And as you can see here, the virtual PFC receives an IP address of 10.0.1.20 from DHCP on our local LAN. So when you run this command in your environment, make sure you substitute this IP address for the address that you receive in your local LAN. So after running this command, make sure you take a look at the output. This is an example of a correctly running Mininet topology. If you see any errors come up, such as Mininet being unable to reach the programmable flow controller, you may want to check sections 1 through 3 to make sure all of your configuration is correct. However, our next step at this point is to configure some Linux host interfaces. Specifically on H1 and H2, we're going to create new tag subinterfaces just to create a more interesting and complex scenario. So I'm going to switch tabs. I'm going to show you the commands to perform this task. So here we have two groups of commands. First, on H1, we're going to create a tagged subinterface, and H1 is going to send traffic using a VLAN ID of 50. And we're going to create on that subinterface an IP address of 192.168.50.1. And then we're going to repeat this process for H2. We'll create the subinterface, and then we'll give H2 an IP address of 192.168.50.2. So I'll show you how to apply these commands in the Mininet prompt now. Just to show you what Mininet is doing in the background, as you can see here, we now have a subinterface with this new IP address. This interface here is the default one created by Mininet, and we're not going to use that for this scenario. And just to show you the change for H2, as you can see from this output, we have no subinterface, and we'll configure the new one now. And as shown by this output, we now have our new H2 subinterface in the new subnet. Now, one thing to point out when you're running this in your local environment, you may see a warning such as this pop up. Recall in section 2, we used Mininet version 2.2.0, which has the 802.1q VLAN tagging module already installed. If you're using an earlier version of Mininet, you may want to think about upgrading or creating the new Mininet version 2.2.0 VM, or you can follow some steps from NEC support in that email you received in section 1 to install this VLAN module. However, if you follow the video up until now, you can go ahead and safely ignore this error message. But at this point, we now have our tag subinterfaces. So if we try to do a ping from H1 to the new H2 IP address, as shown here, you can see that our ping fails. And the reason is there's no OpenFlow rules because we haven't configured anything yet on the virtual programmable flow controller. So what we're going to do next is we're going to show you a VTN configuration that'll allow the PFC to configure OpenFlow on the OpenFlow switch in Mininet. So I'm going to switch tabs and go over to our prompt over here, and I'll show you the working VTN configuration. So as a background, a virtual tenant network, or VTN, is, as the name implies, a virtual network that enables a forwarding behavior on a physical topology. So you can think of it like VRFs or MPLS VPN from the traditional network space. So with this VTN, we want to enable bridging between two hosts in the same broadcast and in the same subnet. So with this VTN, we're going to configure this vBridge, and we're going to assign a VLAN ID of 50 to this vBridge to enable bridging between H1 and H2. So the next step, after we deploy the vBridge, is we need to configure two vExternals. So a vExternal is like a gateway that maps an external host into the virtual tenant network to get the forwarding behavior that we want. So we have vExternal1 for H1 and vExternal2 for H2. And we're using a port mapping technique called OFS map to ensure that we can find or identify H1 and H2. The way this works, so we first need to figure out the switch that H1 is connected to. So we use what's called the data path ID in OpenFlow. And then we need to identify the port. So we're calling the specific S1 port, which is S1-ETH1. And we're specifying VLAN ID 50, meaning any traffic that's received on this S1-ETH1 port with VLAN ID of 50 on this OpenFlow switch will be mapped to this vExternal. And the same process applies then for H2. We simply specify a different port since H2 is connected to a different port on the OpenFlow switch. The last step in the configuration of the VTN is to connect the vExternal to the vBridge via this virtual link. So we create a vlink that connects the vBridge interface to the proper interface of the vExternal. So you can think of this like cabling a physical host to a physical switch. Instead, we're going to have a virtual host, vExternal1, and we're going to create a virtual link that connects it to the vBridge. So to show you how this works, I'm going to go ahead and copy this configuration and apply it to the ProgrammableFlow Controller so we can see it in action. So I'm jumping back over to the console window of the virtual PFC. In order to configure VTNs, we need to drop into the PFC shell, as shown here. Much like other network operating systems, the PFC has a configuration mode and an operational mode. So we need to configure the VTN, and we'll drop into the configuration context. And now we can copy this configuration into the PFC shell. As you can see here, the PFC has a candidate configuration and it has a running configuration. So when you make changes, they aren't applied in real time, they need to be committed. So that's what this command shall do. And as you can see from this exclamation point, we need to save the configuration. And once this configuration is committed, and we've saved the running configuration to the startup configuration, we're now ready to check and verify host connectivity. So we'll run the same ping test from the Mininet prompts. I went ahead and switched to the Mininet secure CRT window. And as you can see here, with the VTN deploy, we now have connectivity between H1 and H2. So as a last step, just to show you some OpenFlow rules, we'll show you a basic OpenFlow troubleshooting step. This command is showing us data flows for the relevant VTN. Recall in this scenario, we configured VTN1 for this scenario. What we're seeing here are the relevant OpenFlow rules for this ping running between H1 and H2. You can see here for match conditions, we're matching on physical port, the VLAN ID, and source and destination MAC, which have been discovered by the ProgrammableFlow Controller. We're using an action that's forwarding those packets to port 2. And this is what's enabling our ping test to work. So this wraps up our section 4 video. We've integrated all of our pieces from sections 1 through 3, and now we have a working software-defined network. To recap section 4, we just completed building our first virtual software-defined network, and we configured our first NEC virtual tenant network. We ran the following 5 steps to complete this section. First, we showed you how to launch Mininet, so you could spin up a single OpenFlow switch and 2 hosts. Second, on the 2 Linux hosts, we showed you how to provision the network interfaces, so you could add additional IP addresses and VLAN tagging for more complex scenarios. Third, we showed you how to configure a layer 2 virtual tenant network to pass traffic between the 2 hosts in the topology. Fourth, we showed you how to verify host connectivity in Mininet to pass traffic between those hosts over the OpenFlow switch and through the VTN. And lastly, we showed you a basic OpenFlow troubleshooting technique on the ProgrammableFlow Controller. At this point, you now have a working virtual SDN environment to try more complex scenarios. In this video, we covered how to build a virtual SDN environment consisting of NEC's virtual ProgrammableFlow Controller. For some next steps to learn more, consult Mininet's documentation to see how to build more complex OpenFlow topologies, and NEC's PFC documentation to see how to build more complex VTNs. We look forward to seeing you in the next video.